Good afternoon, everyone, and welcome to my PhD defense. This work has been carried out in Latim in Brest with co-encadrement. So it's been jointly done in Brest and with also supervision from Liam in Montpellier. The PhD is titled Treatment Planning Optimization for Non-coplanar Volumetric Arc Therapy. So we'll start to see by seeing, I'll make an introduction so we can have some general knowledge about cancer. So I will talk a bit about radiotherapy, and then I will talk about VMAT and what it means and how we move from VMAT to non-coplanar VMAT. And then I'll also present the three main studies that were done during this PhD thesis. The first one about collision detection for non-coplanar VMAT. And then the second one is an algorithm that we presented that is based on symmetric annealing for improving the beam selection treatment planning. And then finally, we presented the other algorithm that we presented during the thesis that is based on rapidly exploring random trees, RRT star. So the variants that the modifications that we made to it, to be able to use it for non-coplanar VMAT. So cancer is a problem that causes a lot of deaths today. It's one of the leading causes of premature death. Here we show a map of different countries in the world and the incidence rate of the cancer. We see that it's a problem that touches several countries at the same time. So we see in the map countries where there's much more red color. It's countries where you have a higher incidence rate of cancer. And we see that it's also much more widespread all over the world. For example, in Europe, we have 2 million people who die from this cancer every year. And it's about 255 new cases every year in France. So it's a big problem, and it's a current problem. So there are several ways that exist to treat cancer. One of them is by surgery, where you have the surgeon who goes and makes a procedure to remove the tumor. There's also targeted therapy that tries to target specific cells in the body to treat the tumor. And the one we'll be focusing on is radiotherapy, which is using external beam to try to kill the cancer cells in the patient using radiation. Or there's also internal beam as well, internal radiation, sorry. There's also chemotherapy as a technique that can be used by injecting anti-cancer drug to the patient. And there's also hormonal therapy that exists that tries to stimulate the hormones in the patient. And these hormones can help to kill the cancer cells or to slow down the growth of the cancer cells. So generally, we focus on radiotherapy because radiotherapy is usually one of the most prescribed treatment modalities for cancer. Most cancer treatments, a large majority use radiotherapy, maybe in conjunction with another of these techniques. In radiotherapy, we try to use radiation to kill the cancer cells. So the first modality that we show on the top right-hand side is brachytherapy, where there's a radiation source that is placed inside the patient. And this radiation source then but the radiation source kills the cancer cells by radiating, radioactive rays. Another modality is the external beam radiotherapy, where you have a radiation source now that is external to the patient. And then by focusing this beam in a specific part of the patient body that has the cancer cells, we are able to kill the cancer cells, and we try to spare the healthy tissues that can exist around this tumor. So the main goal when we do external beam radiotherapy is to deliver radiation to a specific part of the patient body and kill the tumor cells, and then try to avoid putting the radiation on the healthy cells around the tumor. So generally, the external radiotherapy steps are shown here. So we start with the imaging, the 3D imaging. We take the image of the patient. So in this image, we'll have the part of the patient body that has the cancer cells, and also some image of the other organs in the patient. Then there's a segmentation of this image. So during the segmentation, we try to delineate which part of this image that has the cancer and which part that has the normal cells. And then we get the prescription from the treatment physician. So the doctor tells us we have to give this quantity of dose to this patient in this part of the body. So then that's when we come inside and do what we call treatment planning. So in treatment planning, we try to make a plan of the treatment of this patient, and then we deliver this treatment plan. So volumetric modulated arc therapy, VMAT, is one of the modalities for delivering radiation. So it's a treatment planning technique. It's a treatment delivery technique for radiotherapy. So if here we compare IMRT, which is one of the existing treatment delivery technique, with VMAT. So in IMRT, you would have a concentration of different beams, so radiation beams that are in one spot of the body. If we look at the left-hand side, you will see that we have very fewer beams, but they're all concentrated in one spot of the body. With VMAT, we try to spread out all these beams. If you look at on the right-hand side of the image, in the picture, you will see all these beams are much more spread out around the patient. So in this way, we use a lower quantity of monitor units. So we deliver a lower quantity of, we spread out the dose that we deliver to the patient all over the body. And so it's much better for the patient, himself to have lesser secondary effects. But then it's much more complex in planning. The complexity of VMAT is much higher. With non-coplanar VMAT, we move from a single motion of the gantry where the patient couch is fixed. Typically, you would have in the coplanar VMAT, we fix the patient couch and the gantry is moving around the patient. So we move only in a single plane, but then we have a limitation to the organs at risk that we can reach. But in non-coplanar VMAT, the couch is moving at the same time as the gantry. So in this way, we can better spare the sensitive organs that are in the patient because we have much more opportunity to target different parts of the tumor and avoid the organs at risk. So we can have much superior treatment plans. The problem is that we have a huge space of the possibility of the solutions. So we have much more bigger problem that are much more complex problems. So the state of the art that exists for this non-coplanar VMAT, we have manual methods. So in this case, we have the treatment physicians who select manually specific beam orientations and then say, okay, we will deliver the treatment from these beam orientations. So this is manual, it's not optimized. So we don't know if there are better solutions. Of course, there's better solutions. Then we have beam IV methods that try to select using the beam IV of the patient, of the tumor in the patient, the best non-coplanar orientations. But much more recent approaches use the beam angle selection method. So we have algorithms that try to select a set of beam angles that are inherently non-coplanar. From the state of the art, we identified some problems, like there's the risk of the collisions that are not well studied. And usually, most of the methods in the state of the art, they try to limit the space of the solutions that they sample. And usually, during the beam selection, the machine constraints are not considered. And then in the end, you will find that these methods instead of that start to insert an unoptimized beam in order to create a valid trajectory. So for us, our objectives was to determine, to find a methodology to determine collision-free couch gantry orientations that can be used for the treatment. And then we also wanted to propose a beam selection method that considers the machine constraint and can give us that has no limitations in the candidate space that it selects. And we wanted to improve also the trajectory creation to avoid the insertion of intermediate beam orientations in the last stage where we create the trajectory. So we'll go in the first methodology that we presented for collision detection. This methodology, looking at the state of the art, there are some existing approaches. For example, on the left-hand side, we see an approach that is implemented for slicer RT. So it uses the collision detection filter that you can use in slicer. It was proposed by Srikama in 2017. So, but this filter, you can use it by, entering manually a set of couch and gantry angles that you want to test if they have collision. And then when you enter them, then it moves the system to this configuration and it tells you if there is a collision here. Another one is the second one on the left-hand side and the right-hand side, the room eye view approach. So it uses the camera and OpenGL to capture a scene in the room. And then from this, image, it estimates the geometric shapes of the treatment, the equipment, and the patient. And then this geometric model is what it uses to calculate intersection between the shapes that it estimates from here. Of course, we think that there is a better way to do this. For example, we want an automated way to input the couch and gantry orientations to be able to test more couch and gantry orientations. Manually, it's not very easy. And then also we feel that we need the dynamic, we need dynamic you use the dynamic model of the treatment equipment to test for collisions, not the geometric model, because the geometric model for collisions is error prone. So our proposition is to use dynamics of the liner and then to use Adams and MATLAB to do a code simulation, which helps us to detect if there is contact forces. and thus collisions, and it helps us to do this in an automated way. So what we did is we have our LINAC equipment that is installed here in Brest. So it's a variant true beam. So we obtained the 3D model of this equipment, and using this 3D model, we assemble it in Adams. So we obtain the 3D model in different parts, which we can assemble with joints in Adams, and introduce collision measurement elements inside that can tell us if there's a collision between the bodies. So, for example, here on the left-hand side, we have the first fixed frame with R1 and R2. We can introduce a revolute joint between the two of them. And this revolute joint can then, when we send joint values to it, it can rotate the fixed head with respect to the fixed one. So in the end, after the assembly, we have the LINAC equipment in Adams that looks like this on the top left-hand side. And this model in Adams can be compiled to a Simulink plant that we can send a command from MATLAB to this Simulink plant. So the commands that we send as input are orientations. So these orientations will move the system to a specific configuration. And then from there, we can read the force elements as collision forces. We can measure this at the output of this plant. So to test our method, we took 8,800 pairs of couch gantry angles. On the left-hand side, we can see the workspace. So each of these pair, we send it to the Adams plant, and then we read the collision output to see if there's a collision there. On the right-hand side, we see the map that it shows us that, and the blue dots that are plotted show that at these areas where there's no collision in the workspace, so it's collision-free workspace that we can read out. So each of these couch and gantry orientations, they are discretized at 5 degrees separation. So we also tried to, made this experiment using the real equipment to test if what we have done in the simulation is the same as what we get on the real equipment. So we sampled some couch and gantry orientations and see if the orientations, the collision result that we get in the simulation in Adams and MATLAB is the same as what we get on the real equipment. So we see if there's collision in Adams and if there's collision in the real equipment at the same time. And generally, the results show the same, that the simulation and the real equipment agree. So from here, we can conclude that the method that we propose, we can easily integrate it in the pre-planning step of most radiotherapy treatment. So we use the 3D CAD model of the installed radiotherapy equipment. So this is required for any treatment center that wants to use this methodology. And we can have problems with the accuracy. For example, if you have some imaging equipment in your 3D CAD model of your radiotherapy equipment, you have to be, if there are differences between the real equipment and the CAD model, you can have some problems with accuracy. For example, on this map, we see that there are some there's some false, because, for example, you see some areas that are completely surrounded by collision workspace, that you see a collision-free orientation that is completely surrounded by collision-prone orientation, which shows some error in the signal in there. So for us, we want in the future to be able to include the patient model in a study like this so that it can be as much more realistic to the real operations as possible. So the second study that we will present is the study that is used for the non-coplanar VMAT. Is a similar algorithm for non-coplanar VMAT. So the idea is to propose an algorithm for beam selection for non-coplanar VMAT in order to improve it. So in the state of the art, there's existing approaches for non-coplanar VMAT. For example, on the top left-hand side, we see the method that uses a set of coplanar arcs. So what they do, they take a set of coplanar arcs which are non-coplanar to each other, and then they run a VMAT plan on these arcs. And another method uses several grid circles, the one in the middle, that is proposed by Estaville. So they use a grid circle and they run they run the VMAT treatment plan on these grid circles. So you're kind of fixed on these grid circles of how to move around the patient. Then there's the greedy method that is the much more recent state of the art that's proposed by PARP. So in this method, they use the greedy method to select the beam orientations. So in the greedy method, you're always selecting a new orientation as long as it reduces your objective function value. The problem is that when you run into a local minimum, you have no way to go out of it. It becomes the end of your your optimization. So this is the solution. So for us, we found that most of these methods that are in the state of the art, because of the huge size of the problem, they always try to limit the size of the evaluation, the space of. They always try to limit the space where they make the evaluation of for the candidate beams. The size of the space is 4 pi. It's very huge. So they try to always limit this, and most of them did not consider the machine parameters when they select these beams, which is quite important because in VMAT, you are trying to optimize the machine parameters. So for us, we wanted to consider the machine parameters when we select the beams. And also we wanted not to limit the space where we search for the beams. We want to look in every space. So that's why we use the simulated annealing to help us to do this. So our method is to intervene at the beam selection part. That's where we want to modify. Typically, you have 3 steps that look like this in the state of the art, where you do the first beam selection, then you do the trajectory generation in the second step, and in the final step, you have your final VMAT plan. So the modification we are doing is in the first step in the beam selection part. So our algorithm starts like this. We have an input, a set of beams that they are collision-free beams, and then we calculate the dose influence matrix due to these beams. And then at each iteration of our loop, we select a candidate solution. So at random, this is done at random. And then we introduce it into our set of the beams that we use in the treatment, and we run a directly trajectory optimization. Then we check if the objective function value that we end this optimization with is better than the previous one. And then we accept the set of the beams that we have as the best solution. Otherwise, we go back and try to get a new one that helps us to reduce the objective function value. And for here, our stopping criteria, because it's a simulated annealing algorithm, our stopping criteria is in the temperature of the cooling temperature. So for the simulated algorithm, the cooling temperature, for the cooling temperature, we have to select an initial and a final temperature for the cooling of for the cooling of the algorithm in order to ensure that we have a convergence. So we use this formulation in this equation to select the initial and the final temperature. So, for example, we use the maximum change in the objective function value between 2 iterations. But at the beginning of the algorithm, you have to calculate this maximum change in objective function value, which is you calculate the differences, all the different possibilities, and then you take the maximum of the vector. And that's for the initial, and then for the final, you do the same when you're looking for the minimum of the vector. So when you select the optimal beams, you will have beams that are everywhere in the candidate space. For example, on the left-hand side, you have a set of candidate beams that are all red. So you say, okay, we select a set of beams in this space using some algorithm. So those ones will be the blue-colored beams. Each of these beam orientations, the machine has to go from one to the other. You have to reach each of them. Problem is sometimes they're all far apart from each other. So in order to move from one to the other, we cannot have an arbitrary motion of the machine. So we have to introduce intermediate beam orientations, which are the green color ones. So for us, we create a graph structure to be able to do this. So the graph structure holds all the candidate beam orientation. So we create an adjacency matrix in order to represent this graph. And then we run a heuristic algorithm that we use to insert the intermediate beam orientations for this step. So this is a very important consideration in this methodology. So we have an evaluation study that uses the objective function value in equation 4. It's the mean square deviation from the prescribed dose. And we use MATLAB. MATLAB is a MATLAB toolkit that is on GitHub for the computation. It's proposed by the guys in Heidelberg, if I'm not mistaken. It's very important for us because there's not many open source toolkits in radiotherapy research. And also the data that we use is patient data that is quite used by other researchers who are working in this field. So we have the PROCET case and the TG019 case, and people who work on VMAT and non-coplanar VMAT, I'm sure they will be very happy to be able to compare with the data that we use here as well. So this is why we use it, because it's quite comparable across the community. So for the machine parameters, we fix the couch and the gantry speed to be at the same speed, and the dose rate at 600 monitor units, which is typical what we use in the treatment today. So the result we have for the TG19 case, We show in this slide, we have a comparison between the greedy method, which is in the state of the art, the non-coplanar SA method, which we propose, and the coplanar method, which is like the classical VMAT method that is being used. We see that our method shows the non-coplanar SA method, it shows a much more conformal dose. You can see, for example, in the coplanar case, that you have a high dose area of 50 gray that exists outside of the target, which is not what we want. We want the target to have 50 gray and everyone outside to have as much as possible the low dose. We fix the target for the organs at risk, the target dose to be 0 gray. So we see that the more conformity is seen with our method, with the non-coplanar SA method. This TG1 case is quite classical non-coplanar is a simulated non-coplanar case that is usually very difficult to have an optimal dose distribution inside. It's quite good for testing non-coplanar treatments. We see also in the DVH, we have reductions in the mean dose to the core and to the body when we are using the non-coplanar simulated annealing method versus the greedy method. We also see reduction in the mean dose to the core when we are using the simulated annealing method versus the coplanar method. So we see generally that the simulated annealing method shows reductions in the mean dose. And also, when we compare, here we see the dose statistics to confirm the data that we are showing in the DVH. So, for example, we see that the conformity number for the TG1 case is much higher for the simulated annealing method. In the trajectory, we see that the simulated annealing method has more control points. So we have 92 control points when you compare it to the other methods, the greedy method and the coplanar method. So here we get more control points at the end of our trajectory equation. So the prostate case is shown here. The prostate case is also comparing the greedy method, the simulated method, and the coplanar method. You see also that the simulated method follows the same trend. The simulated method has better dose conformity, and the high dose area is really concentrated in the tumor target. For example, if you look at the coplanar method at the bottom, you can see that we have as high as 30 gray outside the tumor, which is not very desirable in this size. If we compare the non-coplanar simulated method, we have that the high dose areas are much more concentrated around the tumor area. And this is also seen in the DVH. We have reductions in the mean dose to the bladder and to the rectum if we compare the simulated method to the non-coplanar greedy method. And if we compare also to the penile bulb, we have reductions in the mean dose as well. So this is what we can see in the DVH. If we also compare the simulated method to the coplanar method, we have reductions as well in the mean dose. We have an increase in the mean dose to the penile bulb when we compare to the coplanar method, because the coplanar method, the trajectory is fixed. So this is an outlier case where you have one organ at risk, which is performs very well on this specific trajectory. But generally, the non-coplanar simulated method performs very well when shown to any different case. So the dose statistics also shows us the reductions in the mean dose that we have. For example, in the bladder and the rectum, we generally have reductions in the mean dose when we use the proposed algorithm. So the proposed algorithm with the trajectory, we see also that the trend is the same. The delivery time and the number of control points is much higher than the other two methods. With the simulated method, we have a delivery time of 127 seconds and 43 control points, which is higher than the greedy method and the coplanar method. So from here, we have some conclusions. We are able to handle the non-convexity of the non-coplanar VMAT problem. This is very important because the VMAT especially has a non-convexity, which is due to the machine parameters. So when you introduce machine parameters in an optimization, you have immediately have a non-convexity. So because we use directly trajectory optimization, we are able to overcome this and to approximate it to at least to a much more convex problem. And we have improvements to the dosimetry with reductions in the mean dose to the organ at risk. So we have seen that when we add the control points in the second stage, we can degrade the quality because we add the beams that we did not optimize in the trajectory, and we don't know how the machine is going to deliver it when it's moving. So we also have an increase in number of control points with this non-coplanar simulated method compared to classical methodologies. The reason is because in simulated annealing, we are trying to select beam beam orientations that are in the candidate space, and these beam orientations could be quite far apart. And so when you have things that are far apart from each other, you try to make an interpolation to reach from one to the other. So you don't know how many you're going to add. So this random process of selecting beams everywhere and trying to interpolate to them cause this. So the future work, we would like to evaluate this on more cases, for example, with more complex cases like the head and neck and the brain, for example. So the third methodology that we will present is the sampling-based approach for non-coplanar beam match that using rapidly expanding random trees. So this approach is presented to be able to handle the problem of where we insert intermediate beam orientations. So we select some beams, and then we start to insert intermediate beam orientations. We want to handle this problem and try to create a trajectory that is, how we can say, much more natural. So it's during the beam selection, we also think about the trajectory. So the existing approach that we see in the literature is the Monte Carlo tree search by Dong. So it's the more recent approach. So this approach tries to select. It defines the beam orientation like nodes. So this node, you try to select a new one. You make some expansion from existing nodes. You then use a value that is called UCT. UCT is a function of the objective function and a function of the node itself to select the next node. So we pick the highest UCT value from all the nodes that are possible to select. And then we make a graph propagation by calculating the new objective function value with that node at the terminal. But in the end, we found that this method only uses the beam orientation for this calculation. It doesn't really consider the machine parameters during this process. So for us, we wanted to find a non-coplanar trajectory by saying, okay, let's minimize the cost function along the trajectory. And then we say we wanted this to have a simultaneous selection of the beams and at the same time a simultaneous creation of the trajectory. So at the same time, we do the two at the same time. We wanted also to consider the machine parameters during this, of course. So this is why we start to think about a method that has a natural implementation of this is in the rapidly expanding random trees, the RT star. So the RT star is shown on the left-hand side, a small illustration of how the sampling process works. So you try to discover new nodes starting from a start node. So we have the P start, which is a start node. So from there, you make a sampling in your candidate space to discover new paths. So you discover the new paths, you make a sample. For example, the P end here is the new node that's just been discovered. We don't know if it's the end, but it's the new one. So from the nearest node on the tree, we make a sample in the space, we discover a new one, and based on some criteria, we can add the new discovered node on the tree. So in the end, you have a tree structure. So this kind of algorithm can handle problems with very, very high dimensions, and it gives you an opportunity to generate a path while you're simultaneously evaluating a path objective. And this is where we think this is one of the main reasons why it's very interesting for us, simultaneously evaluating a path objective. It's been used also in planning trajectories for robots and for controlling complex systems. So it's a probabilistic sampling approach. You start from a point and you randomly sample the space. So the algorithm looks like this. There's an input set of candidate beams that we then put in a graph structure. The graph structure helps us to be able to, for example, run the nearest neighbor algorithm faster. So from the graph, we find a neighbor. So we'll have two data structures. In fact, you have the graph data structure that holds the input candidate beam, and you have another data structure, the tree data structure, where you put the newly discovered nodes. So from the graph, we select an input node, and then we try to steer to the nearest neighbor on the tree from this node. And so from this steering function, we use the nearest node to compute. We use a new node that we discovered to compute the cost function first, and then we use the nearest node as well to compute the cost function, and then try to see if the neighbor node, the cost is less than the cost to the new node, starting from the root. So if this cost is less, we say that the neighbor that is existing on the tree becomes the parent of the new node. So you have an attachment that is done between the neighbor node and the new node. Otherwise, we go back and try to select a node that we can find in the graph to run in the loop. So we have a stopping condition in the algorithm. If you see the stopping condition on the left-hand side, we are using the number of iterations. Interesting thing about this algorithm is that we do not stop the algorithm based on some defined configuration. So the idea is that we don't want to stop the algorithm because the couch and the country are oriented in a particular way. So we want to stop the algorithm. We use number of iterations as a stopping condition. We don't have a defined goal. We have a number of iterations. So we are sure that after these iterations, we stop the algorithm. So we can actually control how it's running. So at the end of the tree construction phase, we then run a depth first search. What the depth first search does is that it goes at each of the terminal nodes on the tree. So we have a tree, you have a set of nodes on it. So these nodes are connected by branches. So each of the branch has a terminal. So the last node on this tree. So you go on this last node, and then you make a recursive, a reverse search. Each node you get the parent, and you go all the way back to the root node. So this, trajectory from from the terminal node all the way back to the root node is a path. So what the depth first search does is to discover all the possible paths on this tree, and then all these possible paths, then you can get the best one based on the objective function value for each of the paths, which we stored during the computer of cost functions during the tree construction. So here, we would like to point out some important things about this algorithm. For example, the choice of the initial node. This relationship is trying to get the first estimate of the first estimate of the objective function. So what we try to do with this relationship is to find the beam orientation that gives us the best improvement to the objective function value on its own at the first iteration. So we have a set of beams. We say, okay, if we take this beam, does it reduce the objective function value best than all the other beams? So this is what this relation does. So it selects one of the beams, and this beam, or we can say node, is the initial one, which we call the root node, where we start the algorithm from. And then the second thing that we wanted to point out is the number of iterations that we use as a stopping condition. So the number of iterations we use the 1/10 of the candidate space. So we have a candidate space of 1,000 something orientations. So we use 150 iterations for the stopping condition. So here we see the algorithm, how it's behaving during the node discovery phase. On the right-hand side, we have a green box, and this green box is the root node. So this root node is where it starts to discover all the other nodes. All the other nodes are the black dots, which are the discovered node that will exist on the tree. So at each iteration, you try to discover a new node and add it on the tree. So when you have discovered all these nodes, you will have a diagram like this. So from this diagram, we see that there are lines that are colored in brown. So these lines that are colored in brown are the branches, what we call branches. They are connections from one node that has been discovered to the other. The discovered nodes are the nodes that are in red color. So, and the terminal node, if you follow one of the branches all the way from the root node all the way to the end, you will see that you end at the terminal node, which is also the red color. So before we run the depth first search, the tree looks like this, and then from each of the terminal node, we run the depth first search all the way back to the root node to get the set of trajectories, and from this set of trajectories, get the best one, and that one is the one we are going to use for the treatment. We wanted also to point out some of the modifications that we have done to the RRT star for our treatment planning. For example, we changed the steering method, the steering from one configuration to the other. Typically, in robotics trajectory planning, you have a steer function that is a function maybe of the robot model that so you use maybe the geometric model of the robot to make the steering. But for our own case, the motion of the linear accelerator, we cannot make arbitrary motion. So we fix the motion to be in 8 possible directions from a given theta. From a given couch and gantry angle, you have a small displacement that you are allowed. So you can say, I move the couch and the gantry theta degrees in this direction, but you cannot move arbitrarily from one configuration to the other. So this is in the algorithm. We change the evaluation of the path objective to be the evaluation of the objective function of the treatment. So we want to move along the path where our treatment is much more optimal. So the path should be the path that minimizes the objective function value for us. So this is different from typical RRT algorithms that we move the path along the low cost, for example, the shortest path algorithms. So this is using the treatment objective. And here we do not have any defined goal configuration again. We're not trying to move the couch and gantry angle to a specific configuration. We are trying to move it along a specific path to be able to have an optimal treatment plan. So the results are shown here. We see that the RRT method, for example, the figure C, we are comparing it to the non-coplanar simulated method that is presented and the existing grading method in the state of the art. So what we found is that generally the simulated method has the best dosimetry. So you see that the simulated annealing method that we presented is much better than the RRT star method that we presented here. But the RRT star method is much better in terms of dose conformality compared to the non-coplanar grading method. So, for example, you see we have in the RRT method a 30 gray high dose area outside the target. If you compare to the simulated method, this is not the case. And also in DVH, we can see also that compared to the greedy method, the RRT method is better. You have up to 40% reduction in mean dose to the core on the DVH on the left-hand side that we see. And on the right-hand side, we have the non-coplanar simulated annealing method versus the RRT star method. You see that we have an increase in the mean dose to the core using the RRT star method. So the non-coplanar simulated annealing method is better than this in terms of the dosimetry. And you can also see this in the dose statistics table. In the dose statistics, you can see that the simulated method is still better. You have a higher mean dose to the core of 7.4 with the RRT star method compared to the simulated method of 4.7. But compared to the grading method, the RRT star method is better. For the trajectory, this is where the RRT star method shows its improvement. We have proposed two metrics for measuring trajectory. We call it the bending energy and the total bending energy. This exists in literature, so it's not something we created, but we are using it now for measuring the trajectory for non-coplanar VMAT. We see that the bending energy for the RRT star method is much better for the simulated method. So which shows that it's a much more, I should say, deliverable trajectory that doesn't have arbitrary motions everywhere. It's the same with the total bending energy. There's not a lot of bend on the trajectory. So it shows that this trajectory is much more deliverable. For the prostate case, we saw the same trend as well. We see reductions in the mean dose to the bladder when we are using RRT star method versus the grading method. So we saw reductions in the mean dose to the bladder and the rectum and the penile bulb. We also see an increase. We also see an increase in the mean dose to the bladder and the rectum when we are using the RRT star method versus the simulated method. So again, the simulated method is better than this RRT star method. So it brought us to the main question: what should be the trade-off? Is it between the quality of the dosimetry or between the quality of the trajectory? Because we take in this case, this is the prostate case that we are comparing. We have the CT slides for the non-coplanar simulated method on the left-hand side and on the RRT star method on the right-hand side. So we see that the simulated method has better dosimetry quality, but the trajectory is much more, it has a higher bending energy. So it has a bending energy of 0.85. So it has several bends to be able to deliver it. And we are not sure if it's practically possible to deliver this trajectory. So the question is, what should be the trade-off? Because the quality of the RRT star method is not as high as the simulated method, but it's quite better than what is in the state of the art. So the decision, the open question is, should we base mostly on the trajectory or mostly on the dosimetry? So what we saw in the conclusion, what we saw is that when we add control points, we can have a degradation of the quality of the plan. So using this RRT method, we can avoid this addition of extra control points. So the improvement in the dosimetry with respect to the greedy method that is in the state of the art, but the dosimetry with respect to non-coplanar simulated method is inferior. So this improved trajectory, there's an improved trajectory as well with our the RRT star method when you compare to the non-coplanar simulated annealing method we have seen. And we say that we can have a reasonable trade-off between treatment plan quality and treatment plan deliverability. This is what this RT-star method can offer us. So we will just talk briefly about the contributions of this thesis. To summarize, we have proposed a method that can improve the collision detection for beam orientation. We have also proposed a similar linear algorithm that can help us to select the optimal beam orientation for non-coplanar VMAT. We have seen by comparing to the state of the art that it improves the dosimetry. We have proposed an RRT-inspired algorithm that can help us to simultaneously generate a trajectory while getting an optimal non-coplanar VMAT plan. And this will help us to eliminate the need to insert intermediate control points. And we have also seen that we have improvements to organ at-risk sparing and to the treatment trajectory quality. So we also made some publications. We have a publication that has been submitted to Acta Oncologica, and then we've made a presentation of this at ICCR in Montreal. And we also made some oral presentations on Labicamex days, Labex days. There's another one that will be presented in Grenoble in December of this year. The challenges, now I'll talk a bit briefly about the challenges that we encountered during this test. This is the published methods are not open source. We have limitations to the memory capacity, and we could not really evaluate the collision detection method for all orientations because of safety restrictions. And when we use proprietary software, we can have additional costs, monetary costs. So for the future work is to evaluate these algorithms, the computation time, the hyperparameters that we use to improve, try to improve on the data storage and the compression. Also would like to evaluate this on more patient cases and also clinically on a phantom to start with. And we think that we can also use the trajectory planning algorithm that the RT-star algorithm, for example, in prostate brachytherapy for trajectory planning. For example, during the needle insertion, we can have a defined node within the prostate, and during the insertion, our job will be to try to meet those nodes and interpolate the motion of the needle during prostate brachytherapy. So this is possible. So thank you for listening.